Thanks, Christian. And as a bonus, I'll also be introducing our new toolbox, CortPro. So let me jump into it. There we go. So there was really an abundance of cortical maps that emerged at the start of the 20th century. And by about the 1950s, it started to become very contentious because there was all these different maps and there was a lot of debates over where were the correct boundaries. And the debate really coalesced into this argument over whether it's really reproducible to base this on just visual inspection. It could really be liable to individual biases then. So there was a really wonderful development of this histological profiling approach. And so Brattenberg was one of the people who pioneered this in the 60s, and he created this more quantitative method to look at how cytoarchitecture and myeloarchitecture varies across the brain. It's really simple. You just look at how the image intensity changes from the peel layer down to the gray-white matter boundary. But this produced a more objective way to appraise different areas, compare them across regions, and etc. So we and others recently have translated this into the 3D realm. And this has been really helpful for both histology and MRI. So for histology, we use 3D reconstructions, just like the big brain, but also like the AHEAD data set. And this is really helpful, obviously, because we can avoid the cutting plane issues, so you can see laminar no matter where you rotate the brain and which cutting angle you've chosen. And honestly, this is a very well-established approach. We're not the only ones doing this. And so instead, I'm going to talk mostly today about this MRI application. But I just want to highlight the histology because the toolbox that we have works on both histology and MRI. MRI, it might be a little bit more contentious or questionable, and that's why I want to delve into it. So here we leverage microstructure sensitive imaging, which is highly scalable. So instead of working with N of 1 or N of 2 or even N of 10, we're working with tens of thousands of MRI images here. And that means it's also compatible with longitudinal tracking. We can do this on people across time, and we can directly compare microstructure to function. So these are really key aspects of investigation that we want to follow up by translating this 3D histological profiling into in vivo imaging. And what we've been doing lately is trying to dig into whether this is a reliable method, basically. So I'm going to touch on 3 points we've been testing, really the validity of this approach, its reliability, and its replicability. So first, a little bit about how do we analyze these profiles. Once again, we borrow innovations from histology. So there was an approach by Schleicher back in, I guess, the 1990s now, where you can analyze the shape of a profile based on its central moments. So on the left, you see a typical profile that we would obtain with microstructure sensitive imaging, something like 0.8 millimeter resolution, for example. I always put like the peel surface at the top and gray-white matter boundary at the bottom. So you just end up with this pretty nice, smooth curve. It's not like histology. We don't have the bumpiness of different cell density as you move through layers, but you do get this nice curve. And so we can still look at the shape of this using the moment-based approach. So these big brains here, you just see the 0th, 1st, and 2nd moment and how they vary across the cortex in a standard healthy human brain. And on the right, you can just see like a sliding window approach to how changes in the moments reflect changes in the underlying profile. And this is synopsized, I think, most easily by these plots on the right. So you see the 0th moment, it's just the mean. So it doesn't actually care about the shape of the profile. It's just like taking the average intensity within the cortex. And the later two, though, the 1st and the 2nd moment, the 1st relates to the center of gravity. So it's sensitive to the balance between the upper and lower intensities. And the 2nd moment is more related to, well, it's the standard deviation across depths. And that in vivo MRI, we find it's related to the concavity of the profile. So if it's flat or if it's a bit bumpy. And what I find really important about this, or helpful, is that the moments actually show different patterns of spatial variation. So always at one end, you tend to get sensory areas that are unique in many ways, but then they pattern the association cortex in different ways. So they're really complementary measures to describe regional variation in the human brain. So let's get into whether this is really a valid approach. Is it similar enough to really say that we're looking at laminar organization, even if we're going to much lower resolution, and the biological specificity is also lower when we use MRI rather than histology? So we started to question, so are these profiles derived from standard research quality MRI sensitive to laminar? And to test this problem, we looked at this really brilliant data set. I think it's from Magdeburg. They scanned one man, tens of sessions, but there's 8 scans that are T1s, and he was scanned for 53 minutes per scan. Apparently, he doesn't move very much in the scanner, so he's like the perfect participant. And from this, they then super sampled this together to have a 250 micron in vivo MRI. And so based on this, we then extracted profiles across the whole cortex from the 250 micron image, but we also downsampled that image to imagine what it'd be like if this is a standard 0.8 or 1 millimeter resolution image. And so in these profiles here, you see in the nice dark blue is this 250 based profile. Really nice bumps, really likely concording to like the stria of Gennari or lines of Ballinger that you see within these areas. As you move to the yellow though, where we're going lower resolution, those bumps really aren't as prominent, obviously, but it still bends in the way of those bumps. And so in the last plot, you see whether the moments across the whole cortex are similar as you move down in resolution. So the 0th moment, yeah, it doesn't care about the resolution. But the first moment, it's still, even at 1 millimeter resolution, it's over 0.95 correlation with the map derived from 250 micron data. And the same for the second moment, it's above 0.9 correlation. So overall, the pattern of regional variability that you get, even at these much lower resolutions, is very similar to the high resolution data. So this helps us, or puts some confidence in for us, that even at 1 millimeter, in vivo MRI is capable of capturing certain features of laminar organization. Even though we're not going to resolve specific layers, there are differences that we're still able to recapitulate at this lower resolution. Okay, next we looked at the reliability. This is basically if you put someone in a scanner on one day and you put them in the scanner the next day, are the profiles going to be the same? Same person, the profile should be the same, there shouldn't be much change overnight. For this, we used a wonderful data set from the Donders where they did so with 17 subjects. They scanned them with both quantitative T1, so an R1 scan, as well as T1 over T2. And we see here on the right the intersession similarity, so how similar it was from day 1 to day 2. And you see for using R1, the moment maps are super duper similar across all the subjects between the 2 sessions. And you see this is the intraclass correlation coefficient across the regions as well. Dark blue means good. In the T1, T2, there is one exception though. So the first and second moment are very reliable, high intersession similarity, but the 0th moment actually has a bit of a drop. And this has been noted in a few papers recently. So people have been using this T1 over T2 as a myelin marker or myelin mapping, but even from the people who kind of advocated for this, like Matt Glasser, have noted that it wasn't really ever intended for inter-individual comparisons because T1 and T2 is not quantitative. If you just look at the image intensity in one person versus another, they might be biased by several different aspects to do with the scanner. So in particular, I won't go into the details here, but it's well known that the transmit field biases are affected by the scanner, but body size and also by the positioning. So you see, for example, one person's image intensities, like the 0th moment, are very different from one session to the next. And this may have been because that person was positioned in the scanner in a different way. So their head was lying in the magnetic field in a different way, and it kind of throws all the measurements off. So you can't directly compare the 0th moment of T1, T2 from one session to another. So for us, this was also helpful, though, because we realized that the higher moments overcome this problem. Because these bias fields have a pretty low frequency, so you can see these bias fields over here. If you look at the balance within the cortex, it has the same bias within that part of the cortex. So by taking the relative effects there, by using the first and second moment, you can kind of overcome some of these issues, and it makes it a more scalable approach. Oh, and we replicate this in a few other studies as well. The final aspect of our testing was about the replicability. So whether you could reasonably assume that you're going to get the same type of maps across different sites. So we looked at the ABCD data set, which had 21 sites of 10-year-olds across the US. We looked at 5,000 participants, and this is T1 over T2. And once again, we find that there is okay, but a bit low replicability in terms of the 0th moment. But as we look at these higher moments, we are looking at the shape of the profile, we see really high replicability, even though these are across different sites. They use GE, Philips, and Siemens scanners. There's a lot of variability there, but it still seems like this is a really replicable approach for us. And for the sake of time, I won't jump into the last one, but it's also about that we could extend this across different types of sequences as well. So to wrap up, there's many different applications we have for this, so I'll just zoom through a few. For example, we've used this to look at neurodevelopment, showing real nuance in the way that the cortex develops during adolescence. We've looked at this to understand the relationship between structure and function, because we can do these tests within a single individual. You can look at their microstructure, you can look at their connectivity, you can look at their functional activation patterns, all within a single subject. And related to that, with 7T data, we can start going really fine-grained here and looking at these beautiful patterns within the regions of how cytoarchitecture varies. So for example, in the parahippocampus gyrus, you tend to see more of a gradient, but in the prefrontal cortex, you can see this pattern of interdigitation. So this has all become possible through this translation of 3D profiling to in vivo MRI, which I hope I've convinced you is a pretty reliable approach to use and could be helpful in several studies. And if you want to give it a go, feel free to check out our toolbox, CourtPro. It's open source, and you can run your data if it's BIDS compatible with just one line of code. And feel free to come talk to me if you have any other questions. Thanks.